everything will work out nicely.
Black pen, red pen, yay!
In this video, I'm going to talk about the idea and the strategy for how to solve a linear differential equation. But before I do this with you guys, let's talk about an integral first. Let me ask you guys this. What's the integral of sine x over x? And I know I did not put down the dx, but it was for good purpose. Anyways, what is the answer to this? And you should know that this right here has no answer, right? This is actually a non-elementary integral. So no matter what you do, use substitution, integration by parts, whatever, the answer at the end is just not going to be nice, right? But what if I tell you that maybe I can add something right here? Let me ask you guys this following integral instead. What if I'm going to ask you guys what's the integral of sine x over x plus ln x times cosine x? And now, suppose this is my actual question I want to ask you guys. I'll put a parenthesis around this and a dx so I can be legitimate. What's the answer to this integral now? Okay, maybe you see it, maybe not. But let me tell you that this right here, it actually has a much better answer. And the answer to this integral is just going to be sine x times ln x. And of course, we are done. And I'll put down a plus c at the end. Well, how come I can just get this for the answer? Well, let's look at this backwards, okay? If you just kind of pay attention to the form, first of all, you see that you have an addition in between of two things, right? And then here we have sine x over x. And then here we have ln x times cosine x. And guess what? If you put this down, you see, sine x times ln x, that's the function part. And if you just go ahead and differentiate this instead, this is how we do integral derivative, right? You put down the answer, and if you want to know if this is the right answer or not, you just have to take the derivative of this. If you can get back, that will be the antiderivative. That will be the integral, huh? You have to use the product rule because this is a product of two functions. And the product rule I want to show you is, well, I will keep the first function, which is sine x, and then we multiply by the derivative of second, which is going to be 1 over x, and then we add. And you see, this is why I know that I will use the product of two functions, because earlier this is the adding situation, right? We add the second function, which is ln x. Yeah, that's a big hint, you see? And we multiply by the derivative of first function. Derivative of sine x is positive cosine x. And you see, we get back to the original integrand. And of course, this will be the antiderivative for that. And that will be the answer earlier, huh? So that will be a way to do integral, right? You just kind of look at the form, and then you're going to just notice that this right here, it actually came from a product rule situation for the derivative. Okay, now, why did I bring this up? Let's talk about the linear differential equation. If you look at this right here, we have, this is the form that you want to begin with. dy dx, which is the derivative, plus another function times y, and y is a function of x. And then you put everything else on the right-hand side. And you see, this is linear because the derivative, okay, it's just to the first power. It's not in the cosine, it's not being squared or whatsoever. Likewise, for the y, it's only to the first power. If you have y squared, if you have square root of y, this wouldn't work, okay? So I'm going to show you guys the strategy of how to deal with this kind of situation. Look at this again. We have the derivative and the original. And I'm going to use this idea again. Let me write it down for you guys. Here is the product rule. I just want to put this down. And I would like to write it down as, if you want to take the derivative of two functions, and I will just use f times g. F is the first and g is the second, of course. And the form I want to write it down for you guys is this. We will keep the first function and we multiply by the derivative second, and then we add the second function times the derivative of the first. This is the product rule, right? And now, I'm going to differentiate this for you guys. You see, we have the derivative and its original. We have the derivative, well, in this case, it would be the g prime, if you want to match like right here, and the original, which is right here. Very similar, right? However, over there, we have an issue because there was nothing in front. And of course, it's not always the case that you have a 1 in front, like as a function-wise. Anyways, I want to just kind of match the form for you guys. Today, I want to differentiate something times y. And I'm not sure what this is yet because I didn't have anything right here. So that's why I just leave it blank, okay? All right, I want to differentiate something times y. You can imagine this actually a function, okay? All right, using the product rule, we will have something times the derivative of the second function, which I will just put down dy dx, so I can match with that form over there. And then we add, well, this right here, I don't know what it is yet, and I'll just kind of like, I don't know, leave a blank. But then the second part is, we will keep the second function, which is y, times whatever this was. And now you see, this is why I put down, for the linear differential equation, I'm looking at the product rule. Once again, I didn't have anything in the front, so that's why I leave a space right here. And then for this right here, it's the one I have to differentiate. All right, now the issue is, seriously, we didn't have anything in the front, and this may not be a good form that we want to use. So this is the idea and the strategy. We're going to use something that we can force the left-hand side here to be the derivative that came from the product of two functions. And what we're going to do right here is that we'll just say we're going to use, and the thing is that we will multiply what we mean by the integrating factor. Okay? So we can force it, the left-hand side, to be the product of two functions, and we have to use the product rule to match that. Well, we are going to use another function, and that's called the integrating factor, and I will label this as mu of x. Okay, so I'm going to kind of just draw a line between this, and this is what we're going to do. We will multiply everything by mu of x. So from here, we will end up mu of x times dy dx plus mu of x times p of x times y. And then on the right hand side, we have to just multiply this and that, and I'll just have mu of x times q of x, just like that. All right, now you see, I'm just going to put down mu of x, right? That's a new thing I want to have. Otherwise, seriously, I just have blanks. That's no fun, right? So the blank will be the mu of x. And right here, let me just write down mu instead of mu of x for simplicity purpose. Hopefully you guys don't mind. Today, if we differentiate mu, which is a function of x, times y, which is also the function of x, we use the product rule. We keep the first function, which is mu, and then for the second part, right here, you see, we will have to differentiate the mu and then put it here. And now you see, we can mix and match the form. Mu of x times dy dx, which is this right here, and then we add it with, we have the y right here that's matched, right? Well, in order for us to come up with a formula for mu of x, what must happen is, you see, mu of x times p of x, which p of x was from the original. It must match mu prime. So the key is, we are going to set this to be mu prime. And let me write this down right here for you guys. Mu of x times p of x, we want this to be, so let's set this to be mu prime of x. Because this way, you will see the left-hand side will be the derivative of a product of two functions, right? And from this right here, we'll be able to come up with a formula to get mu of x. And we will multiply everything by the mu of x, the actual function, and you'll see everything will work out nicely. Of course, I'll show you guys an example with actual functions, so be sure you continue to watch this video. And also, I will suggest you guys to watch another video. It's called the fake product rule. You can click the link in the description. It's a lot of fun, and the strategy right here is very similar, okay? Now let's continue. What I would like to do next is, I would like to divide both sides by mu of x, okay? So that they cancel. And let me write this down first right here for you guys. We will have mu prime of x over mu of x, and this is equal to p of x. And now let's look at the left-hand side. We have the original function in the denominator and the derivative on the numerator. This is a form that came from the derivative of a logarithm, right? In another word, if I integrate this, and the reason that I'm integrating is so that I can somehow get rid of the derivative, right? Anyways, let me integrate this. Of course, we'll have to integrate both sides. This right here is going to be ln absolute value of mu of x. Well, double check. Today, if we differentiate this, the derivative of ln of mu of x, it's going to be 1 over the inside, 1 over the mu of x. And then because of the chain rule, we multiply by the derivative of the inside. That's how we get the mu prime of x. Okay? So the integral of this is equal to ln of this. If you differentiate that, you get that. Don't worry about the plus c. And on the right hand side, I will just write it down as how it is. Integral of p of x dx. And once again, don't worry about the plus c because we don't care about the constant. We just care about the function part. We just care about that function part, so we can multiply the original equation by that function part. Everything will work out nicely. At the end, we see that we have mu of x instead of the ln. What can we do to get rid of the ln? We do e to that, right? So that e and that will cancel. Finally, this is the formula, and let me write this down right here for you guys. To get mu of x, and you don't even need to worry about the absolute value because once again, you can have positive or negative function. Both of them will work. You just need to have one function that you need to make things work. So let me just write down mu of x. This is equal to e, okay? And the power is an integral. You have to integrate p of x dx. This is how you are going to find out what that integrating factor is. And now let me show you guys an example so everything will make much more sense. So let me show you guys how we can solve this linear differential equation with the strategy that we just talked about it. And if you're doing this on your own, you should pay attention to the following. We see that we have dy dx, the first derivative, right? And here we have the y to the first power. There's no other y's, there's no other derivative. This is indeed the first order linear differential equation. So you can use the integrating factor, the one I just showed you guys earlier. Alright, now, this right here, it's not in the correct form though, because we have this cosine of x in the front. But it's okay, because we can just go ahead and divide everything by cosine of x. Right? This way, we'll be able to get into the correct form that we want. We will have dy dx plus sine of x over cosine of x. We can just write that down as tangent of x. And you see right here, I put a parenthesis around the x because we have to emphasize x is the only thing that's inside of the tangent. The y is being multiplied with tangent of x. And this is equal to 1 over cosine of x, which is just secant of x, right? So let's just put that down. From here, we are in business because we can see that the p of x, this right here, is positive tangent of x. From here, we will be able to work out that formula to find ourselves an integrating factor. And yes, you have to know that formula. So right here, let me write it down. Mu of x for that integrating factor is going to be e as the base. And the power is an integral, right? We have to integrate p of x. And let me just write this down for you guys. We have to integrate tangent of x right here in this situation. And let's just go ahead and work things out. First, work out the integral. The integral of tangent of x is ln absolute value of secant x, right? So we still have the e for the base, but this is going to give us ln absolute value of secant of x. Don't worry about putting down a plus c right here or not, because we just need one integrating factor. We just need that function part. The plus c later on, yes, it will be from the process of solving the differential equation, but for the integrating factor, don't worry about it. And in fact, what I'm going to do next is I would just like to cancel out the e and the ln, and I'm just going to say mu of x. Instead of saying absolute value of secant x, I'm just going to use the positive version secant of x. This is it, okay? And the reason for that is, we just need to have one function. You don't want to multiply with absolute value of secant x. You don't want to multiply by negative. Nobody likes negative. Use the positive version, positive secant of x. This right here is a function that we are going to multiply throughout with our equation. Everything will work out nicely. And I know I didn't put down the parentheses right here and right here, but they shouldn't bother you too much, right? Anyways, let's just multiply by secant of x throughout this equation, and let me write this down right here for you guys. You multiply everything by secant of x. And of course, we have to be sure to distribute, and let me put down the result right here. First, we will have secant of x times dy dx, and let me write it down right here. Next, we add it with secant of x times tangent x, right? So let me put this down. Secant of x times tangent of x, and then we still have this y right here. And on the right hand side, secant of x times secant of x, we have secant square of x. Alright, here is the punchline. On the left hand side, this, you see we have secant of x times the derivative y plus y times the derivative of the secant x, right? This right here is nothing but just the derivative of secant x times y. You see, if you go back to the form earlier, this was the mu of x and the y. And once again, you can always write down the derivative and just differentiate it to double check. Derivative of secant x times y is you keep the secant x and times the derivative of y, and then you add, you keep the y right here and you multiply by the derivative of secant x, which is secant x tangent x. So nice. And you see, this right here is just that. We force it to be the derivative of the product of this and that. The right hand side is still the secant square of x, okay? And the left hand side, we have a derivative. How can we get rid of this derivative? Well, we can just integrate, right? And of course, we will have to integrate both sides. On the left hand side, this and that will cancel, and we'll just have this, right? So let's write down secant of x times y. I know this looks sexy, but this is secant of x times y. And then this is equal to the integral of secant square of x. This is just tangent of x. And then right here, I will put down the plus c. And this is because, we are solving that differential equation. This is the constant that we need. All right, now at the end, of course, we want to isolate the y. It's not bad to do, right? But let me just write this as 1 over cosine of x first, and this is multiplied by y, and this is equal to tangent of x. Let me just write it as sine of x over cosine of x, and we still have this plus c. Because if I look at the equation, this for now, we can just multiply everything by cosine of x. This and that cancel out, and we will just have the y left on the left hand side. And then be sure you have to distribute, right? Multiply everything by cosine of x. Cosine of x times this, we will just have sine of x. And then cosine of x times plus c, we will just put down plus c times cosine of x. And this right here is the general solution to that differential equation. And of course, suppose you have an initial value. Let's say if you have this equation here along with an initial value, let's say y of pi is equal to 2. Well, now we can just plug in these values into this form and solve for c. This means x is equal to pi and y will be 2. Now let's just plug in 2 into this y. We will have 2. This is equal to sine of pi, right? Because x is pi. So let's write that down. Sine of pi plus c we don't know yet, and we multiply by cosine of x, which is the same as cosine of pi. And just work this out real quick. Sine of pi is 0, cosine of pi is -1. So this means we have the 2 right here, and this is just 0, and we have just c times -1, that's negative c. And of course, we can just divide both sides by -1. C will give us -2. At the end, if you have this initial value, the solution will be y is equal to sine of x. And here we have the plus c, but you know c is -2, so we'll have -2 times cosine of x. And this right here will be the answer with this initial condition. So hopefully you guys like this.